Look at this question. Solve the given system of equations if the system has non-zero solution. Understand, it doesn't mean that this system, it has only non-zero solution. Definitely, as we know, when it is a homogeneous system, it will have a zero solution also. Correct? So when it has non-zero solution, what may be the value of lambda? I mean, for what values of lambda, this system will get non-zero solutions. That's what your question. Now see, anyway, to answer this, let us first take what you call the matrix form. As we know, the matrix form is Ax is equals to 0, correct? So if you take Ax is equals to 0, the matrix form, you see, you will get matrix form like this. First row, it is lambda 1, 1. Then the second row, it is 1, lambda 1. And the third row, it is 1, 1 lambda. Right? So this is the coefficient matrix, and it is equals to XYZ. Coefficient, I mean the solution vector, and on the right side you have only zeros. Right? Now see, this is what you call your solution vector, I mean matrix form. Now understand it this way. In what case, as we discussed till now, in what case this system will get infinitely many number of solutions, I mean non-zero solutions. Right? You see, if you have rank of A as equal to the number of unknowns, as we discussed, this system will get a unique solution. I'm not interested in that. And when it is a unique solution, that will be a zero solution. Zero solution in the sense x is equal to 0 is the solution. Correct? But see, as we know, to get infinitely many number of solutions, we want rank of matrix A to be less than the number of unknowns. Right? So then you will get infinitely many number of solutions, and all these are what you call non-zero solutions. Right? See, that is what you are exactly expecting. You are expecting non-zero solution to this system, and to get non-zero solution, we want rank of matrix A to be less than the number of unknowns. And see how many unknowns are there here. There are 3 unknowns. Therefore, you can write like this. This system will get, it's a homogeneous system, as you know. So this system will get non-zero solutions. When they are non-zero, they are all definitely infinite only. This system will get non-zero solutions if rank of A is less than 3. Right? Why it is 3 here? Because there are 3 number of non-zero rows. I mean 3 unknowns. Since the number of unknowns are 3, I'm taking this as less than 3. So to get non-zero solutions, we want rank to be less than 3. That's one idea. Recall what is here matrix order. It's a 3 by 3 matrix. You see, when you are given a 3 by 3 matrix, and when you say rank is 2 for a 3 by 3 matrix, if rank is 2, from this you can say determinant of A is equal to 0. You see, I hope you remember this. When rank is less than the order of this matrix, then definitely determinant should be equals to 0. Right? So that's how, since rank, you want rank to be less than 3, you can then say determinant of A must be equal to 0. Right? When rank of A is less than 3, as we know, determinant will be definitely equal to 0. So what you can conclude here, you see, when you are expecting for a homogeneous system, when you are expecting a non-zero solution, then definitely determinant of this coefficient matrix will be equal to 0. Of course, this happens only when the number of equations and number of unknowns are equal. But when you are given a rectangular matrix, I mean, when you have 4 equations and 3 unknowns by chance, right? When you have a system of 4 equations and 3 unknowns, then this idea will not work. Then what you can do in that case, then by taking matrix A, you need to reduce that into its what you call echelon form. And thereby you can find out the rank, and then you can see for what values of lambda you will get non-zero solution. But since you have a chance of taking determinant here, let us proceed with this idea. When your system need to get non-zero solution, then rank must be less than 3. And when rank is less than 3, definitely we need determinant to be equal to 0. Now let us take this determinant and equate it to 0. Now consider this particular point to find out the value of lambda. Now see, what is the question here? You want non-zero solution, so that we need to find certain values of lambda for which this determinant is equals to 0. Right? We need to find a value of lambda such that determinant of A is equals to 0. And understand, for those values of lambda, your system will get infinitely many number of solutions. Even your system will get non-zero solutions, right? Now let us take this lambda determinant to be 0, and thereby let us find the values of lambda. So this implies what you have, you see, determinant of, I'm just taking matrix A here, lambda 1 1, 1 lambda 1, and here this is 1 1 lambda. And now I'm equating this determinant to 0. See, while evaluating the determinant, we know we can evaluate the determinant about any row or any column. But here, let me take the determinant about what you call the first row. So using the first row, let me evaluate the determinant like this. It is equals to, first of all, lambda times. What happens to this, you see? You need to now leave the first row and first column. By leaving first row and first column, we take cross multiplication like this. So it is lambda into lambda, lambda square minus 1. Next, minus. Now we take the second element as 1 into, now we need to leave the first row and second column. Now leaving the second column, you see, we'll get it like this, 1 into lambda minus 1 into 1. So it is lambda minus 1 plus 1 into, now see, now you need to leave what you call first row and third column. Now leaving first row and third column, what you get here, it is 1 into 1 minus 1 into lambda. So it is 1 minus lambda. And you are equating this to 0. Right? Now see, look at these terms carefully. Here it is lambda minus 1, fine. From the third term, by taking minus common, you can rewrite this as lambda minus 1. So in these two terms, we have a possibility of taking lambda minus 1 common. Therefore, even from the first expression, see, I'm writing it like this, lambda times, when it is lambda square minus 1, we can write it as lambda plus 1 into lambda minus 1. Now, right, see why I'm writing this way? Because I can take lambda minus 1 common from now all the three terms, right? So then it is minus, it is lambda minus 1, let it be like this. Now from this, as we discussed, to get a lambda minus 1 here, I'm taking a minus common. So minus of lambda minus 1. I'm equating that to 0. Now see from here. See, as we discussed now, let us take lambda minus 1 common from all these terms. So when you take lambda minus 1 common from the first one, you need to multiply them. You see, lambda into this, lambda square plus lambda. And see here, when you take lambda minus 1 common from that, we'll get minus 1 here. And when you take lambda minus 1 from this, here also we'll get minus 1. So when you add these two, we'll get it as minus 2. And I'm equating this to 0. Minus 1, you know, minus 2. Right. Now see, from this, we'll get either lambda minus 1 is equals to 0 or lambda square plus lambda minus 2 is equals to 0. Right? Now see, this implies, you can write it like this, lambda minus 1 is equals to 0, or how can we write this one? You see, we can write it as lambda plus 2 into lambda minus 1 is equals to 0. Right? This quadratic expression can be written as a product of these two factors, lambda plus 2 and lambda minus 1. Okay. Now from this, we can write lambda is equals to 1 or lambda plus 2 is equal to 0. You see, when it is lambda plus 2 is equals to 0, we can write lambda is equals to minus 2, or if not this, we can write even lambda is equals to 1 again. Right? Anyway, lambda is equal to 1. You can take it only once, right? That's how I'm writing only two values for lambda. One is repeated. So lambda is equals to 1 or lambda is equals to minus 2. Now see, understand, for these two values of lambda, your system will get non-zero solutions. But since you are asked to solve that system by taking these two values of lambda individually, we need to find out the solution, right? So let us take once lambda is equal to 1 and find out the solution. And then in the second case, let us take lambda is equal to minus 2 to find out the solution, right? Let's do it one by one. Now in the first case, see what I'm trying to take. Case 1, if lambda is equals to 1. Now see, if you take lambda is equals to 1, let us first take matrix A. Right, see what you have matrix A, it is all ones except the diagonal elements. And even in diagonal, you have simply lambdas. So there in diagonals, I'm substituting lambda is equals to 1. So that all this matrix becomes simply of ones. Everything becomes 1 now. Now see, this matrix has to be reduced to what you call the echelon form, because you see I have not reduced that to echelon form earlier. So let us reduce this into echelon form from this one. So we can use these operations. R2 changes to R2 minus R1, and along with this you can take this operation. R3 changes to R3 minus R1. So by taking these two operations, see what happens to this echelon form. First row you're actually not changing, so let it remains as it is. Then the second one, see what happens, 1 minus 1 0, 1 minus 1 0, because you know they're all same elements. We'll get both the rows as zeros. Remember, because you're trying to get what you call non-zero solution. As we know, as we already discussed, rank must be less than the number of unknowns. When rank is less than the number of unknowns, there must be at least 1 0 row in its echelon form, right? If all the 3 are non-zero, then what will be the rank? It is 3 again, correct? So, but we want rank to be less than 3. When it is less than 3, you must get at least 1 0 row, right? If there is at least 1 0 row, then only what you did is correct. By chance, while you are solving problems, if you get a non-zero row somewhere, understand, if you get all the 3 as non-zero, understand, you did something wrong somewhere. You need to correct it again. Right now, see, from this, clearly rank of A is less than the number of unknowns, and you can expect, even as we have started, definitely you will get non-zero solutions. In fact, we got lambda values from that step itself. So I'm not writing the ranks and other issues here, but I'm writing only the equations from this, right? What you get the equations, these are the coefficients again. So the coefficients, they are 1 into x plus 1 into y plus 1 into z is equals to 0. And the other two, there are simply 0 rows, so no need to write them as equations. So what you got here, you see, you got only one equation, but the unknowns are 3, right? So when you have one equation, you expect only one unknown, but there are 3. What does it mean? There are 2 unknowns extra compared to the number of equations. So now we need to take those 2 unknowns as arbitrarily. So let me take y is equal to some k1 and z is equal to some k2. Right? I need to take 2 unknowns as arbitrary as you like. So from this, we'll get the value of x as, you know, x is minus y minus z, right? So it is minus k1 minus k2. Right? When it is minus k1 minus k2, you can write the final solution, right? Capital X is equals to, it is minus k1 minus k2, then y it is k1, and z it is k2. So this is the solution when lambda is equals to 1. You can see for different values of k1 and k2, you will get infinitely many number of solutions, right? That's one thing. Now let me take the second one. When lambda is minus 2. Right now here it is lambda is equals to minus 2. See what happens in this case. Now again, in a similar way, I'm taking capital A. What is capital A? Again, as you have seen, except the diagonal elements, remaining all are ones. Correct? Now in the diagonal elements, in place of lambda, we are taking minus 2. So this is minus 2, here it is minus 2, and here this is also minus 2. Now let us reduce this into what you call its echelon form. If not that, you can directly use minus 2. It is all up to you. But for my convenience, I'm just exchanging R1 and R3, so that I'll get a 1 in the first place. Now, so then it is equivalent to what you get here. You see 1, 1, minus 2 in the first row. The second row, it is 1, minus 2, 1. And now the third row, it is minus 2, 1, 1. So when you have a 1 in the first row, first column, you know, the calculations become easy for you, right? For that, I've just exchanged this. Then R2 changes to make this 1 in the second row as a 0. R2 changes to R2 minus R1. And then R3 changes to, see here it is a minus 2. And in first row, you have a 1 there. So when you multiply the first row with 2, you will get a plus 2. And if you can add that to third row, we'll get third row first element as 0. So it is R3 plus 2R1. So that you see 2 minus 2, it is 0. Now with these operations, you will get a new matrix as this one. You see you're not actually changing the first row, so let it be like this, 1, 1, minus 2. Then the second row, R2 minus R1, 1 minus 1, 0. Then minus 2 minus 1, it is minus 3. Then 1 minus of minus 2, 1 plus 2, it is 3. Right? Next, third row, you see, you are multiplying R1 with 2. 2 into 1, 2 minus 2. First element is 0. Then 2 into 1, 2. 2 plus 1, it is 3. Then 2 into minus 2, minus 4 plus 1, it is minus 3. So we got this one right. Now this is your new matrix. Now see, using the second row, second element, we need to make the next element, third row, second element as 0. So for that, we can use this operation as we know, R3 changes to R3 plus R2. Now see, with this operation, what happens? It is equivalent to first row, it is 1, 1 minus 2. In the second row, we are not actually changing, 0 minus 3, 3. And the third row, will, when we add R3 and R2, we'll get this third row as completely 0. Right? See, again, as I told you, by chance, if you didn't get this third row as a 0 row, you should understand you did something wrong. Because for this value of lambda, we have already verified, we must get non-zero solutions. But see, if this is a non-zero row, we'll get only a unique solution. Right? So keep that in view. And now from this, let me write only the equations. So the first equation is x plus y minus 2z is equals to 0. And the second equation, minus 3y plus 3z is equals to 0. Right? Now see, you have only two equations, but there are three unknowns. When you have two equations, you normally expect two unknowns. So there are three unknowns, which means one unknown is extra. So let us take that extra unknown z as k. Right? So from, let me give some numbers to these two. This is 1 and this is 2. Therefore, from second equation now, what happens? You will actually get 3y is equals to 3z, which implies y is equals to z. So therefore, from this, you can write the value of y as also equal to k. So y is equals to k. Now see, from first equation, now see here from first equation, you can write the value of y, I mean x, as 2z minus y. So this implies 2k minus k. So this implies x is also equal to k. So therefore, if you finally write the solution at the end, a capital X is equals to, it is k, y is equals to k, and z is also equal to k. Right? So that's how you will get the values of different solutions for different values of k. And this is how you can find out the solution in the case of this homogeneous system of equations. Look at this question carefully, what it is. Show that the only real number lambda for which the system of this system has non-zero solution is 6, and solve them when lambda is equal to 6. See, understand this question has two different parts. First of all, we need to prove that the only real number which gives a non-zero solution for this system is 6. Probably there are other numbers, maybe they are complex. Okay, and that is first half of the solution. And in the second half, by taking this lambda is equal to 6, we need to find out the solution also. Right? Normally, you see what students do in examinations. When this question was asked in the examination, students directly substitute the value of lambda as 6 and find out the solution. But that, you know, in case if this is a 10 marks question, you won't get 10 marks for that solution. We need to solve both parts of the solution. You need to write both parts of the solution. I mean, first we need to prove that the real number is 6, and then you can find out the solution. Okay, so keep that in view, and I'm allowing you to unmute yourselves. They're already allowed. See, look at the system carefully. Is that homogeneous system or non-homogeneous system?
Non-homogeneous.
Good. Others? Any others? Is that homogeneous or non-homogeneous? Look at it carefully.
Homogeneous.
Same student, huh? Two different answers. See, let me clear you again. To be non-homogeneous, when you write it in matrix form, we write it as Ax is equals to b, correct? Remember, we are concentrating on this right-hand side vector, capital P. We simply said, you know, when this b is not equal to 0, it is non-homogeneous. When it is 0, we said it is homogeneous. But remember, when you write this in matrix form, matrix B should consist only constants, not the unknowns. Right? It should have only what you call constants. When these set of constants is 0, when you have all the constants as 0, it is homogeneous. When you have at least one constant as not equal to 0, it is non-homogeneous. But look at this system, it consists of, there is something on the right side, it doesn't mean that it is non-homogeneous. But see, when you have that right hand side values as constants, it is non-homogeneous. See, but this right hand side, they're all unknowns. The right hand side terms have unknown, they've included unknowns, x, y, z, right? So when you have unknowns on the right side, still there is a possibility of rewriting the system. What you can do here, you see, look at the first equation, there you have lambda x on the right side and x on the left hand side. You can send this x to the right side, to the other side, you can send this lambda x. So what happens when you take it to the other side, we'll get it as x minus lambda x, right? There are other terms anyway, 2y, 3z, they'll be as usual. Now see, when you take x common from these two terms, you can rewrite the term as 1 minus lambda into x, right? In a similar way, from the second equation, if you take lambda y to the other side, right, what happens to that? You see, you will get it like this, y minus lambda y, the second term. But the remaining two terms, they remain as they are. Now from this again, if you take y common, we'll get it as 1 minus lambda into y. In a similar way, from the third equation, you will get it as 1 minus lambda into z, right? So you can rewrite the given system in this way. And let us see what happens when you rewrite this. You can then see whether it is homogeneous or non-homogeneous. See what I'm trying to do, I'm rewriting it, you see, like this. First equation, when you send lambda x to the other side, we can write it as 1 minus lambda into x plus 2y plus 3z is equals to 0. Right? I've sent lambda x to the other side, therefore I'll get a constant which is 0. Now from the second equation, it is 3x plus 1 minus lambda into y plus 2z is equals to 0. Then from the third equation, 2x plus 3y plus 1 minus lambda into z is equals to 0. Now look at this carefully. Is that homogeneous or non-homogeneous?
Homogeneous.
Absolutely homogeneous, right? So this is what you need to understand. To be homogeneous, there must be some constants and they must be 0. Every constant to be 0. But whereas in non-homogeneous system, you may have constants as non-zeros, right? You may have some constants as non-zeros in different equations. But to be homogeneous, every constant in every equation, there must be 0 only, right? That is the only difference. Antegani, right hand side ఏదో ఒకటి నాన్ జీరో థింగ్ ఉంటే అది జీరో, అది నెంబర్ అయితే ఓకే, కానీ అన్నోన్ కూడా మనం అక్కడ ఉంటే అది నాన్ హోమోజీనియస్ అని చెప్పొద్దు. రైట్ హ్యాండ్ సైడ్ వాల్యూస్ ఉన్నంత మాత్రాన అది నాన్ హోమోజీనియస్ అవ్వదు. రైట్ హ్యాండ్ సైడ్ నాన్ జీరో నెంబర్స్ ఉన్నప్పుడు మాత్రమే నాన్ హోమోజీనియస్ అవుతుంది. ఓకే, సో కీప్ దట్ ఇన్ మైండ్, అండ్ దిస్ ఈస్ క్లియర్లీ ఏ హోమోజీనియస్ సిస్టమ్ ఆఫ్ ఈక్వేషన్స్. అండ్ అండర్స్టాండ్ ద క్వశ్చన్. What you need to prove here, for this homogeneous system, the only real number which gives non-zero solution is 6, right? So if you have a non-zero solution for this homogeneous system, that exists for real number lambda is equals to 6. In fact, that is the only real number. There may be other numbers, but they may be complex, right? Let us see. Anyway, to find out whether it has a non-zero solution or not, or to check further other issues, we need to first write its matrix form, right? Can you tell me what is its matrix form? First, we'll write all the coefficients, the coefficients of x. In the first equation, it is 1 minus lambda, then 2, then 3. Then from the second equation, 3, 1 minus lambda, 2. Then from the third equation, you see it is 2, 3, 1 minus lambda. Right? See, this is matrix A. Then the coefficient matrix is done. You see what happens next. Solution vector, it is x, y, z. Then the right hand side values, you see now, these are zeros, right? Now see, this is what we are actually speaking. When you write matrix B, either you have zeros or other non-zero numbers, but not what you call unknowns, right? When you have unknowns on the right side, you see that is not the right way of writing what you call matrix form. You can send them to the other side and then you can rewrite the matrix form. But now see, we got what you call matrix A here. Now, as we discussed in the previous problem, we are again expecting a non-zero solution even in this case. So for a homogeneous system, when we get what you call this non-zero solution, whenever, any idea? We want now non-zero solution. So whenever the rank of matrix A is less than the number of unknowns, then only we'll get a non-zero solution, right? So the same thing I'm using here also. Therefore, this system will get a non-zero solution. May not be one, but so many solutions. If rank of A is less than the number of unknowns, that is 3. When rank is less than the number of unknowns, as we discussed in the previous problem, determinant will be equal to 0. Right? Whenever rank is less than the number of unknowns, then in that case, determinant of matrix A must be equals to 0. Right? Now let us just consider this determinant equals to 0, and then you can find out it. And then you can find out the solution. Consider determinant of A is equals to 0. That implies determinant of A is equals to, see, I'm writing matrix A here. It is 1 minus lambda, 2, 3. And then it is 3, 1 minus lambda, 2. Then here it is 2, 3, 1 minus lambda. And I'm equating this determinant to 0. Right? See, 1 minus lambda is equals to 0. This implies, see, I'm again evaluating the determinant about the first row. So that what you get 1 minus lambda into, now I need to leave what you call the first row and first column. So it is 1 minus lambda into 1 minus lambda minus 3 into 2. So we'll get it like this, you see, 1 minus lambda whole square minus 6. Then minus 2 times. Now leave this first row and second column. Leaving first row and second column, see what you get, 3 into 1 minus lambda, then 2 into this 2. So we'll get it like this, 3 into 1 minus lambda minus 2 into 2, 4. Then plus 3 times. Now leave what you call first row and third column. By leaving first row and third column, you see what you'll get. It is 3 into 3 minus 2 into 1 minus lambda. So it is 9 minus 2 times 1 minus lambda. And we are equating this to 0. Right? So then this implies, I'm just writing it again, writing it by expanding these terms. See what you get, 1 minus lambda into, if you expand this, see what happens. 1 minus lambda whole square, you see 1 plus lambda square minus 2 lambda. And here is a minus 6, let me write in this order. Lambda square minus 2 lambda plus 1 minus 6. Then minus 2 into, if you just multiply them, we will get them as 3 minus 3 lambda minus 4. Then plus 3 times 9 minus 2 plus 2 lambda is equals to 0. Right? See, this is what we need to still simplify. I'm just writing everything as it is in the next slide as it is. You see, the same thing I've written here. Right now, see, here I'm simplifying this. This 1 minus lambda, I've written it as it is. Then lambda square minus 2 lambda. And here it is 1 minus 6, you see. 1 minus 6 is minus 5. Then minus 2, I've written as it is. And see what it is. Minus 3 lambda is, I've written as it is. Then 3 minus 4. When it is 3 minus 4, we'll get it as minus 1. Then see. Then see this 3 minus 4, it is minus 1. Next in the third term, you see 3, it is carried as it is. Then when it is minus 9 minus 2, we'll get it as 7 plus 2 lambda. I'm equating that to 0 again. Now see, I'm now multiplying these two. 1 minus lambda into this. See what happens. Right, see, I'm multiplying like this. 1 into this lambda square minus 2 lambda 5. So that's how you see what I got. Lambda square minus 2 lambda minus 5. 1 into these 3 terms, we'll get these 3. Then minus lambda into lambda square, it is minus lambda cube. Then minus lambda into this minus 2 lambda, it is plus 2 lambda square. Then minus lambda into minus 5, it is 5 lambda. So that's how I'll get all these 3 plus 3, 6 terms. Then see what you have. Then minus 2 into minus 3 lambda. When it is minus 2 into minus 3 lambda, it is 6 lambda. Then minus 2 into minus 1, it is plus 2. Right? We got these two. Next, 3 into 7, it is 21. Then 3 into 2, it is 6 lambda. I've just multiplied each with other term in each individual terms there. So that's how I got all these things. Now let me write these things one after the other. First of all, I'm writing minus lambda cube. See, I've written minus lambda cube. Then if I write lambda square terms, here it is 2 lambda square plus here it is lambda square, you see. 2 lambda square plus lambda square, you see, I got it as 3 lambda square. Next, lambda terms, minus 2, then here it is 5. Minus 2 plus 5, 3. 3 plus here it is a 6. 3 plus 6, 9. 9 plus here it is a 6 again. 3 plus 6, it is 9. That's how 9 plus 6, it is totally 15 lambda. See what I've done. Minus 2 plus 5, 3. 3 plus 6, 9. 9 plus this 6, 15 lambda. Next, if you write the constants, see here it is a constant 21. 21 plus 2, 23. 23 minus this 5, 18. You see, we have considered all the terms. And this is the cubic equation what we got here. Now see, to find out the roots of this cubic equation, either we can use a calculator or we can use what you call a synthetic division method. You see, what you can do here, synthetic division. We can take all the coefficients here, right? They are minus 1, minus 3, sorry, plus 3, 15, 18. Now see, already are given lambda is equal to 6 is one of the solutions. So let me just randomly take that 6 lambda is equal to 6 here. So what happens, you see, when you take lambda is equal to 6, initially we take this as 0. So minus 1 plus 0, it is minus 1. So then 6 times minus 1, it is minus 6. 3 minus 6, it is minus 3. Then 6 times minus 3, it is minus 18. 15 minus 18, it is minus 3. And 6 times minus 3, it is minus 18. That's how you got remainder as 0. So that's how you see what it is. When you have lambda is equal to 6, when you have these kind of expressions, this is the coefficient of lambda square, this is the coefficient of lambda, and this is the constant. That's how you see. Now this expression can be written as lambda minus 6 into, see, I'm taking these things, minus lambda square, minus 3 lambda, minus 3. Right? See, this cubic expression can be written as product of these two terms. And now from this, when these two terms are equal, the product of these two terms is equals to 0, either of those two may be equal to 0 individually. That's how, see, I'm equating either lambda minus 6 is equals to 0, or see, I've taken minus common from these two terms. I mean, these three terms. When I take lambda common from them, I'll get this expression, you see, lambda square plus 3 lambda plus 3 is equals to 0. Right? Now, since these two are equal to 0, we can write the values of lambda as lambda is equal to 6, or here I'm using what you call, it's a quadratic equation, correct? So I'm using what you call discriminant form. Lambda is equal to minus b minus 3 plus or minus b square, which is 9 minus 4ac, 4 into 1 into 3, which is 12. So we got under root 9 minus 12 divided by 2a, which is 2. Therefore, we'll get lambda is equal to 6, and lambda is equal to, see here you have a 9 minus 12, which you got, which gives you a negative number under root. When it is negative number, you see, we'll get it as a complex number here, root 3 into I, right? And see, that's where the question is. Therefore, the only real number which gives a non-zero solution to the given system is lambda is equal to 6. In fact, you got other two values, but see, those two values of lambda gives you what you call complex numbers. So that's how you are saying the only real number which gives a non-zero solution to the given system is lambda is equal to 6. So this is the first half of your solution. Now let us take the value of lambda as 6 and find out the solution. So when you take lambda is equal to 6, look at the system. You have 1 minus lambda in the diagonal elements. So if you take lambda is equals to 6, see what happens to matrix A. Therefore, if you take lambda is equals to 6, we'll get matrix A as 1 minus 6 minus 5, 3, 2. So the first equation is this actually, not 3, 2, 3. Then the second equation, 3, 1 minus lambda 2. So we'll write it like this: 3, 1 minus lambda minus 5, 2. And the last equation you see 2, 3 minus 5. 1 minus lambda is minus 5. Now see, this is your matrix, and now we need to reduce this into its echelon form. See, how can we reduce this into its echelon form? By using these operations. R2 changes to, since they are prime numbers, clearly I'm multiplying one with the other. I'm writing it like this, you see, 5 R2 plus 3 R1. I'm multiplying R1 with 5 and second row by 3. Sorry, I'm multiplying R1 with 3 and second row by 5. So that we'll get both numbers as plus 15 and minus 15. So when we add them, we'll get it as 0. In a similar way, for the third row, a similar thing can be done. Again, 5 is a prime number, right? So I'm just taking a kind of cross multiplication. So it is 5 R3 plus 2 R1. Right? So for convenience, let me just proceed like this. I'm not changing anything in the first row, so let it be like this: minus 5, 2, 3. Then the second row, what you have there, it is 5 R2 plus 3 R1. I need to add these two, correct? So see what it is. 5 R2 means, 5 R2 means it is 15 minus 25 and 10. Then 3 R1 means minus 15, 6 and 3 3 is 9. So if you add these two, we'll get it as 0, minus 25 plus 6, it is minus 19, and 10 plus 9, it is 19. So the second row elements are 0, minus 19 and 19. Next, similarly, if you look at third row, what is third row here? It is 5 R3 plus 2 R1. So let me just write these rows here. 5 R3 means it is 10, 15 and minus 15. Right, second 5 R3. Sorry, this is minus 25. Next, 2 R1 means minus 10, 2 to the 4, and then 2 times 3, it is 6. So if you add these two, minus 10 plus 10, it is 0, then 15 plus 4, 19, and then minus 26 plus 6, minus 25 plus 6, it is minus 19. So therefore, the third row is 0, 19, and minus 19. Right, so it's still not in echelon form. Let's now make this 19 in the third row as a 0. So that can be done with this operation. R3 changes to R3 plus R2. In R2, there is a minus 19. So because of this, see what happens to the next row. Minus 5, 2, 3. First row remains as it is. Then the second row, it is 0, minus 19 and plus 19. And when we add R3 and R2, we'll get completely this third row as a 0. So right here you are, this is in echelon form. Now see, from this echelon form, let us write what you call the equations, because see, I'm not again interested in writing the rank and writing it has infinitely many solutions, because we got this echelon form after substituting a particular lambda, and you got that lambda when we consider non-zero solutions, right? So it is a clear story. So I'm writing only what you call the equations from this. So if you write the first equation, it is minus 5x plus 2y plus 3z is equals to 0. Then the second equation, you see 0. Then minus 19y plus 19z is equals to 0. Let's see, you got only two equations, but there are three unknowns. When you have one unknown extra, we need to take that unknown as arbitrary. So I'm just taking z is equals to k. Right, so when z is k, what happens to y? You see, if we give some numbers to these two, they are, let us say, 1 and 2. Then from second equation, what you have there, it is 19y and 19z is equals to 0. So you can write it as 19y is equals to 19z, and this implies we can write as y is equals to, just erase this. So this implies you can write y is equals to z, and therefore y is also equals to k. Now see, if you substitute these two in first equation, therefore from equation 1, how can we write this? You see, 5x is equals to 2y plus 3z. 5x is equals to 2y plus 3z, and this implies 5x is equals to 2k plus 3k, 5k. So therefore, this implies even you can write x is also equal to k. All right. Therefore, the final solution capital X is equals to k, y is equals to k, and z is also equal to k. So that's how you can find out the solution for this particular problem. Remember, first we have proved that the value of lambda is equals to 6, and then by substituting lambda is equals to 6, we have calculated the we have obtained the solution, right? So that's how for every homogeneous system of equations, when it has these kind of lambdas and all, we need to use this idea of using determinant of a is equals to 0, and then you can find the required values of lambda, and then you can find out the solution at the end. But if you are given direct questions, if you are given a direct homogeneous system of equations, we need to reduce that into its echelon form, and then by calculating the rank, we can observe whether it has a unique solution or infinitely many number of solutions, right? So that's a story.